Again, welcome back. And just to give a quick recap of what we have done in the last class, we looked at the design principles when we're trying to design sequential circuits, especially circuits that needs to be synchronized with the clock, where clock acts like the synchronization signal. A good practice, a rule of thumb, is that you don't want to introduce any components in the path of the clock, okay? Because that may desynchronize things, desynchronize operations in a large complex system. So that was one thing that we have looked into in the last class, and we looked at the drawbacks of the ripple counter in that sense, and we also looked at how do we construct a synchronous counter that can that can counter that drawback. All right. So we looked at the design of the synchronous circuit by looking at by examining the output that we want. Okay. Each of the flip flop, again, we designed it using the flip flop, the JK flip flops. However, in this case, not all of the JK flip flops were were configured in the in the toggle state, right? Uh, because we wanted it to be designed as a synchronous circuit, we made sure that each of the flip flop was powered by the master clock, was timed by the master clock. Okay, so each of the flip flop was connected to the master clock, and then we examined each of the output of the flip flops, each of the output of the counter that we need, and we modified the configuration of each of the flip flop correspondingly. So that's the approach that we have taken, which is, I would say, which is not a very intuitive approach. It will it turned out that for the synchronous counter that could count up or count down, it's fairly understandable, but for a more complex version, it may not be all that straightforward. Okay. Anyway, but regardless, we did look at the design of a synchronous counter, and then we talked about the state machines. Again, this is what we're going to continue our discussion on. That will be the last topic in our class in the semester. Sequential circuits. Your state machines are sequential circuits, and in the last class, state machines, right? We looked at the example of a human being itself as a state machine, where we considered the emotional states of the human being as different states that the machine can exist in, right? And we also talked about the concept of a state diagram. So we identified the states. That was the first thing, the first exercise that we did was identifying the states that a person can exist in. And if I want to represent, if I want to look at the person, the behavior of the person as a snapshot, then we can basically, represent that in the form of what is called a state diagram. The state diagram. And what is a state diagram? Again, it basically includes all the different states that the machine can exist in. And it also includes information on how the state transitions happen from one state to the other state, right? So the state information or the state itself is represented using the circle, okay? And the state, so let's say going beyond emojis now, let's say I designate this as state 0, S0. I designate another state as S1, all right? And then I'll show the state transitions using this format, using basically these arrows going from one state to the next, okay? And we also discussed in the last class what those arrows indicate, right? These arrows indicate that the arrows indicate the state transitions, which are facilitated by time. It is the time, the movement of time that facilitates those state transitions. And what determines those state transitions is the present state itself. I need to know what state I am in at the present instance. What are the inputs acting on the state at that present instance, right? So that could be some input acting on the state. Let's say some input x equal to some value, some value. That will take me to S1 state, and x equal to different value, let's say value 1. I just want to generalize it at this time. X equal to different value, value 2, for example, maybe taking it back to the same state. This is analogous to, for example, I'm in a happy state, and a happy input acts on me at that present instance. It takes me back to the same happy state, right? So something like that. Okay. And we can complete the state diagram. The way I would complete the state diagram is, first I identify all the states of the machine. Identify all the states that the machine can exist in. Machine exist in. And then I would go to each state individually. Okay. For example, I start with the 0 state. Okay. And I would look at all possible combinations of the inputs. All possible combinations of the inputs. And for each combination of the input, I would draw the state transition. Okay. So go to each state, one state at a time, identify all possible combinations of the inputs. Combinations of the inputs. For each combination, for each input combination, again, your inputs can be many, right? For each input combination, because it's the present state and the input combination that determines the next state. Draw the state transitions. Okay. That's how you complete the entire state diagram. Okay. Now, oftentimes, or in fact, most of the time, you will see that when we're trying to design a sequential circuit as a state machine, using the state diagram approach or the state machine approach that we're going to see, it is this step that are the most critical step. Okay, just like in the K-map also, we saw that the K-map is just a technique. Now, the most important thing given problem statement is, how would you identify coming up with the level 0 diagram, and then identifying the inputs and the outputs and how the outputs are related to the inputs. And once that information is done in the form of a truth table, and everything else, the rest of the steps are pretty straightforward. It's just basically going through some sequence of mechanical steps. You don't really have to think there. But the thinking process happens in the beginning, right? Where you're identifying the inputs and outputs, number of inputs, number of outputs, relating the outputs to the inputs and so on. That's where the most thinking happens. And exactly analogous to that, when you're trying to design a state machine, most of the thinking happens at this step. Identifying the states. What are those states that this machine can exist in? Okay. Next, what are the inputs that are acting on this state? And coming up with this entire state diagram. Once you're done with the state diagram, rest of the following steps to actually realize a circuit that can actually implement that state machine are pretty straightforward, as you will see. Once you follow the process that is taught, then you should be able to do it easily. Okay? But these are the most important steps or stages where you really have to think through for the problem, to solve the problem. Okay. Now, in the last example or in the last class, we looked at the more abstract example of human beings as a state machine. Now we can actually let's try to translate those ideas into designing an actual state machine, a digital circuit that can exist in multiple states. Okay, digital state machine, if you will. Okay, these are also called finite state machines, or in short, FSMs. Finite state machines. Again, you're trying to finite state machines, as in you're working with a state machine that has finite number of states. Okay, now what we're trying to do is trying to translate the ideas into the design of a a state machine. Now, when we are trying to design a machine that can exist in multiple states, a machine that can exist in multiple states, that can exist in multiple states. These are some of the things I need to be, cognizant about. Number one, how do I define the states? What does this mean in the first place? Right? Now I'm trying to design a digital circuit. That means even the state information should be encoded as a binary value. So that means if I have binary value, if I come up with a design of a state machine that consists of, let's say, 5 states. Let's say I want to design some state machine that consists of 5 states. Okay, let's say let's number them as 0, S1, S2, S3, and S4. So I have 5 states. Okay, and because these are digital circuits, and digital circuits only can understand zeros and ones, right? That means even my state has to be encoded. Each of my state has to be encoded with a unique binary value. Encode these with unique binary value. That means if I look at that binary value, if I'm looking at the state information, if I'm looking at that particular binary value, I would know what that machine, what state that machine is existing in at that particular instance of time. Okay. All right. So when I have 5 states, how many binary bits should I be using to encode each state? I have 5 states. I have to encode each state with a unique binary code. So I need at least three binary bits, right? And the variables that encodes these states are called state variables. So the variables that encode or that point to the particular state, each state, are called state variables. So let's say A, B, C are my state variables. Okay. So I would encode, let's say, S0 as 0, 0, 0. So when I go and look at the value of the ABC, if I find that value to be 0, 0, 0 at a given instance of time, that means I know that that particular machine at that particular instance is existing in S0 state. Likewise, I can encode S1 as 0, 0, 1, S2 as 0, 1, 0, S3 as 0, 1, 1, S4 as 1, 0, 0. Okay. And again, these values give the state information. So my state variables are the ones that encode the state information. All right. Okay. So that's one thing. So everything has to be in terms of binary. My inputs have to be in terms of binary. In the last class, when we talked about, I'm in a given state, and an input happens, environment, some kind of event happens. We talked about in terms of events. In this case, those events are nothing but inputs acting on the system, right? Now, in the example of the human being in multiple states, right? We are self-aware of the state that we are in. Again, so basically, if somebody has to tell me what state I am in at that particular instance of time, most likely he may have to look at the chemical makeup in my brain uh, to guess what kind of state I'm in at that particular instance of time. So that will be how that will be analogous to your state variables, right? You're looking, in this case, you're looking at the state, the value on the state variables to know which state that particular machine is at that given instance of time. Okay. Second, my events acting on the state are the inputs. Of course, in this case, my inputs are binary. I can have multiple inputs, but each input can only take binary values, 0 and 1, right? So events acting on the state, these are inputs, they're also binary. Okay, now let's look at arbitrary state diagram. Okay. So these were my state variables. Now when I draw an arbitrary state diagram that consists of 5 states, let me call it S0, S1, S2, S3, S4. So that's a state machine that consists of 5 states. Again, that's an arbitrary state machine. So I'm just going to draw some transitions randomly. Let's say a single input is acting on the state machine. Let's say x equal to 0 takes me back to the same state. X equals 1 take me to the next state. So again, the way I'm proceeding through this, I go from each state individually, look at all possible combinations. Since I only have one input here, the only combinations are x equal to 0 or x equal to 1, right? So S1, let's say x equal to 0 takes me there. X equal to 1 take me back to 0. It can be any arbitrary combinations. I'm done with S1, S2, let's say x equal to 0 takes me there. X equals 1 take me here. S3 equal to 0. X equal to 1. Finally S4, x equal to 0, x equal to 1. Okay. Again, that's an arbitrary state diagram. There's no particular meaning to that. I can implement that, but again, there's no really particular purpose for that state machine. Just as an example. Again, the important thing here is, I would like to reiterate that my present state, and the input in that particular instance determines what my next state will be. So if I'm in the present state, input of x equal to 0 happens when I'm in this particular state. Then in the future instance, in the future time, as time moves, I'm going to remain in the same state. Whereas if I'm in this particular state, and at that instance the input of x equal to 1 occurs, it's acting on my state, on my machine, then in the next instance or in the future time, I will be in the S1 state. Okay, so the present state, because this is very important, present state and the present input determines my future state. Now, when I'm trying to translate the ideas of a state machine from a human being to this design, like an actual physical machine that we can design. Now, for us, we feel time, right? We are built so that we can actually feel the passage of time. What about machines? How would I introduce timing? When I say future state, how can the machine find itself in a future state? What should we do? Any ideas here? Ultimately, we need to design one. If a machine has to exist in multiple states, right, that means it has to progress forward in time. If there is no element of timing there, then we cannot design a machine that can exist in multiple states. It's always frozen in one state. Does that make sense? So what is the thing that we need to incorporate here that would give a sense of timing? Absolutely, clock. So somehow we need to incorporate the concept of clock into the design so that the passage of each clock pulse would take the machine forward in time, right? So when I say here, my present state and the present inputs determine my future state, when I want to reiterate that same statement with respect to the clock, what it's saying is the present state and the present input determines what my future state will be in the next clock transition, in the next active edge of the clock, because that's the next active edge takes my machine forward in time, right? With every new active edge, it's taking that machine one step forward in time. So the clock, absolutely right. All right, so with that information, let us try to draw a basic block diagram for a state machine, what it would look like. Okay. Recall that my state information itself is encoded as binary values. My state variables are the ones that encode the state information. Okay. All right. So with that, so we won't need this one. So in place of that, let's try to draw the general block diagram of a state machine. Now, from what we have written there, what I see is that, let's say, because my present state values are encoded as in my state variables, let me say A, B, C are my state variables. Okay. My present state combines with the present input. So let's say this is my X, the input X. You can have multiple inputs, but I'm just going to draw a single input just for clarity here. But you can have multiple inputs. You can have more number of state variables than just 3, as I've depicted here. Okay. So I'm combining my state variables or my present state that are encoded in my state variables with the present input, producing what my next state should be. So these are combined in whatever ways to produce what is my next state. I represent the next state as A plus, B plus, C plus. Okay. Producing some output, Y, say. And remember, my next state, I'm in a particular state. I have some event acting on me that determines what my next state should be, right? And time takes me to the next state, the passage of time. So I move forward in time. And the next state, once I move forward in time, becomes my present state, right? The future state, as time moves, becomes my present state. So this state has to become, this indicates the present state. These values indicate the future state. Right? And in the future time, because in this example, as we have seen, it is the clock that takes the machine forward in time, right? That means I need to incorporate somehow a clock into this. So the way I will do that is by basically by synchronizing everything with using the D flip-flops. So each state variable will have its own D flip-flop. Let's say that's DA, DB, DC, and that's connected to the clock. Again, I'm not representing the clock attached to each of the flip-flop, but you can imagine that this clock is also applied to DB and DA flip-flop as well, although I just show that for DC only. That's where I'm applying the clock. That's my QA, QB, QC. Okay. All right. So present state combines with the present input. That's my present input. producing an output, and determining what future state I'll be in. What is my future state? And then as the clock, let's say these are my active edges. As the clock proceeds in the next active edge, my future state should become my present state, right? So I need to have this feedback. My future state, which is again, remember these are D flip flops. My output follows the input. So the future state, once the clock moves forward by one active edge, becomes my present state. So that's why we feature this feedback. All right. All right. And that's it. So that's basically intuitively, you can actually build up this block diagram, right? Based on what we have observed. And if I want to construct that, this is how you will be constructing it as. So make sure that you actually remember this the basic or the general block diagram of a state machine, because this will be very useful, very handy when you're actually designing these state machines. Okay. All right, so that's how it is. That's the basic block diagram. Now, when it comes time to actually design a state machine, all it boils down to is, because these are standard circuits, because these are D flip flops. I can remember that I can use any flip flop. I used D flip flop for the initial examples because my output simply follows the input, right? Output follows the input. I don't have to do much there, and that's why I use the D flip flops in this example. Although you can use other flip flops as well. For example, you can use JK flip flop as well to design a state machine. Now, as you will note, each state variable contains its own flip flop. Okay, so the number of flip flops you will need, the number of flip flops in your design that you will need is equal to number of state variables, not states, state variables. In this case, I have 5 states, 3 state variables. I have 3 flip flops. So the flip flops are the one that contain the state information. Okay. All right. So now with this setup, I have a machine that can move forward in time. Okay. Depending on what is being applied on the input, what is the state it is existing in, that determines what the next state is. And in the next active edge, the future state, because I'm entering the future, becomes my present state. My present state combines with the input at that instance, determines the next state, and so on. So that basically continues forward in time. All right. What else do we need to note down here? Yeah. So in the design of a state machine, once you know how the block diagram works, how the block diagram should be, it boils down to the design of this particular block, right? Because all the connections other than this, everything is basically standard. You have this some state variables, next state, flip flops. You don't have to design them; they are there. You just represent them, and everything is done. So the only thing that you really need to do is to design this block. So your design basically of a state machine boils down to the design of this combinational block. This is nothing but a combinational block. So all that you have learned so far, right, you can still apply. This is nothing but a combinational block. You're not doing anything new here. Okay, just have to design this combinational block using the K-map approach. So you can imagine that you will still be working with truth tables in the design of this combinational block. Now, if I were to say, so this for the design of the combinational block, this will be your design level zero diagram. Right? You have identified what the inputs are for this combinational blocks, which are the x, the state variables, and the outputs are y in the next state. So you write down the truth table for them. So these are the outputs, those are the inputs, and you obtain the combinational circuit design combining these outputs to get your these inputs to get your corresponding outputs. Okay. Okay, so that's good. Any questions on this? Does that make sense?
So, is there four inputs and four outputs, or?
Sorry? Yeah, for this particular circuit, if you think of this as a combinational block, this will have 4 inputs, 4 outputs. Although we don't call them outputs, we call them the next state, but it doesn't really matter. It's still considered as an output in the design of that combinational block.
Okay, thank you.
Mhm. All right. Now, as I mentioned before, the most I would not say the difficult thing, but the most important thing or important stage in the design is identifying the states. So let's actually work with some examples and get accustomed to, you know, getting some insight into what are the states and how to identify those states. So again, this is a very important diagram. Make sure you take a good note of that. And then once we are comfortable identifying the states, then we can actually talk about constructing a state machine. Oops. All right. So let's start with the D flip-flop. Let's consider D flip-flop as a state machine. Okay. A D flip-flop. As a state machine, okay, it has a D input, it's one input D. Okay. You have clock applied to this. You have Q, one output. And that's your D flip-flop, right? That's your enable input. And if I want to draw the state diagram of D flip-flop, how would I do it? Number one is what should correspond, what should be the state? What should I take as a state? Take to represent the state of the D flip-flop. To represent the state of a D flip-flop. Now, just like what we have seen in the design of combinational circuits, where we use the K-map approach to simplify the functions, you can design a state machine with the most optimal way of designing it. When I say most optimal, that means you can design a state machine using the fewer number of states. Okay, because the more number of states the state machine has, the more complexity the circuit will have. Okay? So the idea is to come up with a way to design a state machine with the fewer number of states. Okay. Although we are not going to really talk about that in much detail here in terms of optimizing number of states that a state machine has, but at least that's something that you should keep in mind when you're trying to design this, trying to minimize the number of states that a machine could exist in, and yet getting the same functionality out of the machine. All right. So what should I take to represent the state of a D flip-flop? Okay. How about in this case the value on Q? My D flip-flop can exist in a 0 state or a 1 state, right? My Q can only take 2 values, 0 or 1, at any given instant of time. So if I take Q itself as to represent the state of a D flip-flop, let's say I configure S0 as a state where my Q is 0, S1 as a state where my Q is 1. So I have 2 states for this D flip-flop based on the value on Q. Okay, and let me see if I can draw the state diagram for this. I have 2 states, S0, S1. What are my inputs to the state machine? I have one input. My inputs are D, right? I have single input D. Let's say, and then let's try to now draw the state diagram for this. All right. The way I will do this, again, I will go to each individual state, look at all possible combinations of the input. So let's say I go with the S0 state first. So let's say I'm in S0 state. At that present instance, I am in S0 state, and an input of D equal to 0 occurs when I'm in that state. What should be my state transition now? How should I transition to a future state if I'm in this particular state, an input of D equal to 0 occurs? I would represent that again using the arrows. So how should that arrow go? Should the arrow go from S0 to S1, or should the arrow be in the same state, going back to the same state with the input of D equal to 0? What do you think? Going back to the same state, right? With D equal to 0, my output follows the input. If I apply D equal to 0 when I'm in this state, Q was 0, and in the next clock transition in the future, I would be expected to be in the same state, right? So with this, with D equal to 0 should take me back to the same state. Okay? Because these arrows represent how my future transitions will be. In what state I'll be in the future, in future, or in other words, in what state I will find myself in, or the machine in the next active edge. So I'm applying a D equal to 0 when I'm in this state. In the next active edge, or when the next active edge occurs, what will be my new state? I'll be remaining in the same state, because for the D flip flop, the output follows the input. Okay. Again, the other possibility here is D equal to 1 condition, right? So let's say I'm in a 0 state, and the input D equal to 1 occurs now. D equal to 1 occurs. So in the next active edge, or in the future, what state will I be in? Would I go back to the same state, or would I be transitioning to the S1 state? Eric, what do you think? You should be transitioning, right? You'll be transitioning to the next state. D equals 1. Okay, good. All right, so now I'm done with S0 state. I looked at all possible combinations of the input. D equal to 0 is done. D equal to 1 is done. I don't have to worry about any other inputs here. So now I go to S1 state. Okay, and I will do the exact same thing. Now, at this present instance, I'm in S1 state. That means my output of that flip-flop is 1. An input of D equal to 0 occurs. I'm in that state. In future, what will be my future state? Or in the next active edge, how should this flip-flop transition? How should this state transition? Should I remain in the same state, or should I transition to the 0 state? Those are the two possibilities here, right? I'm in the S1 state, an input of D equal to 0 occurs. What should be the state transition now?
Uh, D equals to 0, back to SO?
Back to SO, that's it, right? Because that's the D flip-flop. D equal to 0. When I'm in the S1 state, D equal to 0 takes me back to S0 state. Right? So in the next active edge, because my D flip-flop output follows the input, because the outputs, I've defined my states to represent those, so I transition back to S0 state. So I'm in S1 state. The other possibility is, of course, the D equal to 1 possibility. I'm in S1 state. An input of D equal to 1 occurs. In the next active edge, what is expected to happen? S2. Do I have an S2? I have not defined an S2 state here, right? I only have two states. Stays at S1. That's correct. It stays at S1. S1 because in the present state Q equals 1, my the input acting on the state is D equal to 1. My output follows the input. So in the next state, I remain in the same state of q equal to 1. Okay, and that is my D flip-flop, the state diagram of a D flip-flop. Has two states, S0, S1, and based on the input, these are the state transitions for that particular flip-flop. All right, so let me take a pause. Let me see if you are good so far. Does that make sense? This is very important. How you assign the states. Okay. Okay. Victoria, do you have any questions? Are you able to follow through so far? Okay. So now let's move forward and let's do an example for or draw the state diagram for a JK flip-flop. Okay, let's see what we get. So we've done for the D flip-flop. Let's look at for the JK flip-flop. Again, it boils down to how should I represent the states for a JK flip-flop? What should I consider as states for a JK flip-flop? For a JK flip-flop, I have two inputs. J and K. What about the states? How should I configure the states for a JK flip-flop? Any ideas here? Again, for a JK flip-flop, I have one output. I can still consider S0 and S1 as my states of a JK flip-flop based on the outputs of the JK flip-flop. Right? The output of a JK flip-flop can exist in either 0 or 1 state. Right? So I can still go with the same logic. But the only difference here is I have two inputs. Unlike for a D flip-flop, I only had one input. In this case, I have two inputs. Okay, I have two states, S0, S1. Again, S0 corresponds to a state where the output of a JK flip-flop is 0. S1 corresponds to a state when the output of a JK flip-flop is 1. Okay. Now let's try to complete the state diagram of a JK flip-flop. I have two inputs, J and K, that are acting on my flip-flop. And I go to S0 state. I look at all possible combinations of my J and K inputs. Okay. What are the combinations? I have 0, 0, 0, 1, 1, 0, 1, 1. So these are the combinations of the inputs for a JK flip-flop. And based on this combination, again, this is basically the characteristic table we already know. 0, 0, 0 corresponds to the memory state or corresponds to the same, the output does not change, right? That's what is called the memory state in the future. 0, 1 corresponded to the reset state. 1, 0 corresponded to the set state. 1, 1 corresponded to the toggle state, which is q prime of t. So if it was 1 before or 1 in the present instance, that means in the next clock transition that goes to 0. If it's 0 in the present instance, the next clock transition that goes to 1 for the toggle state. Okay. All right. Now let's go to S0 state, look at all possible combinations of the inputs, draw the state transitions, and then we'll go to S1 state. I'm in S0 state. That means my output of the flip-flop is q equal to 0 at the present instance. Let's consider j equal to 0, k equal to 0. Input acting on S0 state. What do you expect for the transition now? With j equal to k equal to 0, should I remain in the same state? There are only two possibilities for the state transitions, right? Either because I only have two states, either I remain in the same state or I transition to the next state, or transition to new state. Let me call it new state. For j equal to k equal to 0 input, when I'm in S0 state, what should the state transition look like? Should I transition to next state or a new state, or should I remain in the same state? What do you think? Okay, very good. So remain in the same state because that's the memory state. With g equal to k equal to 0, if I'm in this state, with these inputs, I remain in the same state in the future as well. So j equal to k equal to 0, I go back to the same state. Okay, so I'm done with this particular combination. I'm in a 0 state and an input of 0, 1 occurs with j equal to 0, k equals 1. Again, should I remain in the same state? Should I move on to a new state? For this condition 0, 1, j equal to 0, k equals 1.
I think we're staying.
Sorry?
I think we're staying.
Staying, that's correct. That's correct. So let's not worry about S1 state at this time. Let's move on. Let's finish S0, then move on to S1. Okay. Stay in because S0 corresponds to the state where my output Q equal to 0. With 0, 1 on J and K respectively, my output should be 0 in the next active edge. Since I'm already 0, I would remain in the same state. With J equal to 0, K equals 1. That's good. What about 1, 0? I'm in S0 state, that means my output is 0 at the present instance. Applying an input
Now
of
it
j equals 1.
returns back.
Sorry?
Now it transitioning back to S1.
Yes, now it has to transition because S1 is the state where my Q becomes 1. Right? So with j equals 1, k equal to 0, in the next clock transition in the future, that means in the future clock transition, my output should be becoming 1, which is defined by S1 state. That's why with this particular combination of the input, j equals 1, k equal to 0, I would transition to S1 state. And finally, with 1, 1, with j equals 1, k equals 1, what should be my state transition? That means I'm in a 0 state with j equals 1, k equals 1, input acting on this particular state. Would I remain in the same state or should I transition to the new, new state? Transition, right? Because I toggle 0. If I'm in this state and I apply 1, 1 on my JK flip flop, then in the next clock transition that you toggle, right, you should become 1. That's why I go to the next state. J equals 1, k equals 1. So now I'm done with the S0 state. I looked at all possible combinations of the inputs. I'm done with S0 state. I move on to the S1 state now and do the exact same exercise on S1 state. So now we should be able to do it quickly. So now I'm in S1 state. So that means my S1 is the present state I am in right now. And an input of 0, 0 occurs when I'm in that state. And that should, so that means because 0, 0 corresponds to the memory state, that means if I'm in that particular state right now, in the next clock transition, I should remain in the same state because that's how memory is defined. So I would remain in the same state. With j equal to 0, k equal to 0. With 0, 1, 0, 1 corresponds to the next state being 0. So my present state being 1, my q equals 1 state. If 0, 1 occurs when I'm in this particular state, that means in the next clock transition or in the next future clock transition, my output should become 0, right, according to this characteristic table. And that is specified by a 0 state. That's why I would transition from S1 to S0 with j equal to 0, k equals 1 input. What about 1, 0? I'm in this state right now in the present instance. That means my Q is 1, the output of the flip-flop is already 1. 1, 0 occurs when I'm in this state. What should be my state transition now? State. Perfect. If I stay back in the same state. J equals 1, K equals 0. And finally, with 1, 1, I'm in S1 state in the present instance, transition. Perfect. Because that's a toggle state. If I'm in this state, with that input, I need to, in the next state, I should be basically, my output should toggle. I basically toggle. And that's it. Right? And that's the truth table, or that's the state diagram for a JK flip-flop. Okay. All right. Any questions on this? All right, very good. So now let's try to build this state state machine from the. So now let's actually try to build, try to get to um, the mechanisms behind going from a state diagram to actually realizing a circuit. So once you're done with this, this is the most important step. Once you're done with the state diagram, you will see that the next of the steps, if you just follow the protocol, if you follow the sequence of steps I'm going to elaborate now, you will get the answer. Okay, so that's the standard format now. Okay, so let's do that. So so now what I will be doing now is I got the state diagram. I would translate this information and tabulate it in the form of a state table. So this is how you would be, uh, doing your state table. This is the format for the state table. Okay. Okay. So the state table should have these columns in the state table. Let me see. So you have your present state. That will be a first column. Input. When I say input, that means the present input that is acting on your system. That should be a next column. Next state. Third column. And the output, if you have any output. Again, for a state machine, you need not have any output. Okay. But in this case, we don't have, for example, an explicit output. Outputs are determined by the state itself.
Okay, here's a real quick question. So, so on the exam, if you ask the output, we gonna consider output or not?
Can you repeat that?
Okay, let's say an exam. Okay, let's do a JK flop and just put the numbers of how many inputs and outputs in that,
Mhm.
and we're gonna consider Y as an output or
So for this
just
example, the way we have defined it, my state itself are the outputs, right? So I don't really need another explicit output for this. However,
Mhm.
you may have state machines, as you will see later on, with explicit outputs. So just hold on to that thought. That's a good thought. Okay. But for this particular example, we don't have an explicit output. So I don't have to have an extra column here. That's what I'm saying. I don't have to worry about that for now.
Okay.
Okay. But there are state machines which will have explicit outputs, in which case I would have an additional column called outputs. That's what I meant.
Oh, I see. Okay. All right.
All right. So present state. Okay. How and I have two states. How many state variables should I have? State variables. Is it one state variable or two state variables? How many state variables should I have here? One, okay. What about the rest? What do you think? How many of you agree with one? Fabian? How many state variables do you think we should have here? Two, okay. So there's one answer is one answer is two. Okay. Now again, remember, my state variables encode the state information. If I have two states, right, I need to encode each state with a unique binary code. So how many binary bits should I use to encode two states? Should I use two binary bits to encode two states? Should I use one binary bit to encode two states? When I say encode, that basically means yes. When I encode, it's as if you are uh, giving an address to a state, right? Giving some kind of a unique code to the state. So when it's only one state or two states, I only have one binary bit, right? I can encode S0 as 0, S1 as 1. Okay. So S0 is encoded as 0. So I need a single state variable A, let's say. S0 is encoded as 0. S1 is encoded as 1. Okay. So my present state is represented as A. I have two inputs, J and K for this one, right? So let me call that J and K here. And my next state, again, remember that in my general block diagram, if I want to draw the general block diagram, it looks something like this. I have a single state variable A, two inputs J and K, right? That's A plus is my next state. Because I have a single state variable, that means I need to have a single flip-flop, DA, that's QA, clock, and you have the feedback, right? So this will be the block diagram. Of course, we need to know exactly what this block contains, right? So we need ultimately the entire state diagram or the entire design of the state machine boils down to the design of this combinational block. If I want to design this combinational block, I would come up with the truth table because that's a combinational block. I come up with the truth table that relates my inputs for this particular block, which are J, K, and A, J, and K, and the output for this particular block, which is A plus, right? That's what I need to design now. So let's look again. So that's basically a truth table. We look at all possible combinations between A, J, and K. Those are all possible combinations. And I will now refer to my state diagram to populate this table. Okay. All right. Now remember, when my A is 0, this corresponds to S0 state. Right? That's how I define my S0 state to be. That's how I encoded my S0 state as 0. Likewise, this 1 is a 1 corresponds to S1 state. Right? When my state variable features a 1, that means that particular machine at that given instance is in a state of 1, in a state of S1. Okay. All right. Now, A of 0, input 0, 0. That means I'm in present state of 0 or S0. Input of 0, 0 occurs. What is my A plus? What is my next state? What is my next state? So 0, input of 0, 0 takes me back to the same state. So my A plus is still 0. I basically get these values from the state diagram here. Okay. Likewise, 0, 0, 1. That means I'm in the present state of 0. Input of 0, 1 occurs. It's 0. Where is 0, 1? This was 0, 1, right? Input of 0, 1 occurs. That takes me back to a 0 state. That's still 0. 0, 1, 0. That means I'm in a 0 state. Input of 1, 0 occurs. 1, 0 takes me to S1 state, which is encoded as a 1. That's fine. Present state of 0, input of 1, 1 occurs. Present state of 0, 1, 1 takes me to S1 state, which is encoded as 1. 1, 0, 0. I'm in S1 state. With input of 0, 0 takes me back to S1 state, so that's 1. 1, 0, 1. 1, 0, 1 takes me to a 0 state, so that's 0. 1, 1, 0. 1, 1, 0 takes me back to the same state, that's 1. 1, 1, 1. 1, 1, 1 takes me to a 0 state as my future state, so that's 0. And that's it. So now I have populated the table, and now the remaining step is basically to obtain A plus as a function of, as a combinational function of A, J, and K. That's it. And you're done. And let's do that using a truth table. Yeah, so now we don't need this table anymore, or this diagram anymore, because all that information is now presented in the form of this table. I don't need this anymore. Now let's take the K map for this. Between A, J, and K, those are the inputs. Those are the inputs to this combinational block. So what do I have? I'm finding for A plus, the function for A plus. I have 0, 0, 1, 1, 1, 0, 1, 0. So that's 0, 0, 1, 1, 1, 0, 1, 0, right? Yeah. And then I would basically combine them. How do I combine them? Combine these two, and these two, right? And what do I get? Yeah.
Do you really need the second part?
The second part. Oh, you know,
Yes.
you're right. You don't need it. That's a non-essential prime implicant. You're absolutely. That's a good catch. I don't need that because I'm accounting for all the ones just by with these combinations. So I don't really need that additional one.
Extra credit?
There you go. And now I'll write down for A plus. What do I have for A plus? That's A prime J, right? Or, and here I have A
K.
K prime.
K prime, yeah.
K prime. That's it. So now I can connect these. That's A prime J right, so that's A. I need to prime that. Yeah, A prime J plus AK prime. K prime, A, and then and that's my A plus. Okay, this kind of congested here. Let me actually put it down here. Okay, so what I have here is essentially dA clock. That's QA. I also have QA prime, although I do not show it. It's a D flip flop. I can also get QA prime from there. Okay, and what I have here is this is nothing but my A plus. Remember, that is my A plus, right? A plus is connected to dA, so that's nothing but my A plus. So that's A prime J. Remember, what is my A? From this diagram, my A is nothing but QA. QA is A, right? Because they are connected together. That's nothing but QA. That's my future step, a future state variable. And in the next clock transition, that becomes my present state variable from this diagram. So that's A prime, right? So that's A prime J. So I have J, A prime J plus plus AK prime. So A K prime. Of course, I have this. And that's it. So now I've derived my JK flip-flop. And you will observe that this is nothing but what we have, what we have come up with before. This is exactly what I introduced to you, without really telling you how we got that in the first place. But with the state machine approach, now we have shown that this is exactly how that should look. So that's JK flip-flop, derived from a D flip-flop. Okay, does that make sense?
Yes.
Okay, very good. So what I would like you guys to do is, I would like you to practice this because these are very important examples that will get you rolling for your next assignment. Okay, close your books and try to see if you can come up with your D flip-flop design, your JK flip-flop design using this approach. Okay, ultimately, what is important is how would you define your states for those machines. Okay, all right. Now we're almost out of time. Let's see if we can do one more state diagram for a simple circuit. Yeah, let's actually do it for a counter. That will be simple enough. What kind of a state diagram should a counter have? Let's say if I want to draw the state diagram of a counter. A counter that counts from 0000, all the way to 1111 and back to 0000. If I want to design this using the state diagram approach or the state machine approach, first of all, I need to come up with a state diagram for a counter, right? A state diagram. Any ideas on how to represent a state diagram? What should be the states for the counter? How many states should I have? Right. Let's say these are QA, no, QD, QC, QB, QA. Okay. Now with that hint, what do you think should be how should you represent the states for these?
Maybe a fork.
four states, you mean? Or
Yes,
four
like
state variables?
S0 state variables S0, S1,
Okay.
S2, S3.
Oh, states, you mean? S0, S1, S2, S3. Okay. What should be the state transitions now? Why not represent each count itself as a state in this case? Each count itself as a state, in which case my counter now S0, for example, is a count. My counter stays in each count, right, for one clock cycle. That means if I want to represent a state diagram for a counter, that means I have a state. How many states would I have here? I would have 16 states, right? 16 states where in each state, each count itself is a state, and my counter basically progresses through this sequence with each clock pulse, clock transition. Again, this is an example where I don't have an explicit input. It's just going with each clock pulse with new active edge. It's just going through each of these states. S2, S3, S4, so on, S15, and back to S0. So here's a counter state diagram. Now that I have the state diagram, I should be able to translate that information into a state table. My state table in this case, I don't have an explicit input, which is fine. I have four state variables, right? Because I have 15 states or 16 states. That means I need to have at least four binary inputs to represent each state, which are represented, as a matter of fact, the count itself represents the binary code for that state in this case. Okay, so I have the present state, the next state in my truth table, and then you obtain the next state values as a function of the present state values, and then you get your synchronous counter. So we'll take this example up again in the next class, and we'll see how we can design a synchronous counter using the state machine approach. So now the other implication of this is I don't have to have a counter that goes in this particular sequence. I can have any random count. Let's say if I want to have a counter that counts from 0000 to 0110 as a next count, and then some arbitrary random count. I should still be able to design that using this state machine approach. Okay. All right. So now let's wrap this up, and let me see if you have any questions about any aspect. So basically, as you can see here, we are trying to put together all the concepts that we have learned throughout the course in the design of these sequential circuits. Okay. So we are done with the building blocks. It's time to put together these building blocks to design more complex circuits, more fun circuits, I would say.
Okay. First, did you decide on the test day, the final test date?
Yes, it's posted on Blackboard. So please check that. It's on the
Okay.
finals week, Thursday, December, no, not December, April 29th at noon. Make sure you note down the time.
Uh-huh.
Okay.
So that's the problem for me because I'll be already left to the